Hello everyone, my name is Seiji. The theme of this video is the 10-hole harmonica. In addition to just playing a diatonic scale, the instrument allowed special playing techniques such as pitch bending, lowering the pitch, and overblowing, raising it. The skilled players use these techniques to play chromatic scales on this diatonic harmonica and to perform jazz, blues, whatever with greater expressiveness. I'm not a good player, but let me demonstrate pitch bending. On hole 4, you get C on the blow and D on the draw. If you change the shape of your mouth while drawing, the pitch drops continuously from D by a semitone or so. This is draw bending. What about blow bending? On hole 7, you get high C on the blow and B on the draw. Using the same technique, you can lower the pitch from C. I wish I could here demonstrate overblow myself, but I can't. It's very difficult. So I will let Howard, the legend of overblowing, do this demo.
I'll do it on the C right now. I'm blowing on the 6th hole blow, which is G here. And this higher note popped out.
That was an overblow on hole 6, which normally gives G on the blow and A on the draw. But as he mentioned, B flat pops out on the overblow. There's no continuous pitch change in this case. Because he is really good, he can jump directly from G to B flat, but normally a brief silence or a choke occurs between the two notes. All of a sudden, here is the highlight of this video. I'm going to demonstrate the synthesized sound of these. First, draw bend. Next, blow bend. And overblow. Funny thing is, I can simulate an overblow, but when it comes to actually playing one myself, no luck even after a serious exercise for a couple of months. Anyway, let's get back to the talk. We first reproduced the pitch bending in an experiment, which was essentially the same as the one Johnston performed in the 80s. Here is a setup. A cylindrical tube is connected to one of the holes. Hole 7 in our case. And air from the compressor is sent through to make the harmonica sound. We measure the sound frequency while changing the tube length. The results are shown on the right. The horizontal axis is the tube length and the vertical axis is the frequency. You can see that the pitch bending occurs periodically. This suggests that the tube resonances are involved in pitch bending. The bend goes from C down to a pitch slightly above V. The way the bend occurs changes somewhat when the tube diameter is varied across these three cases. Here is the proposed sound production model. The simulation variables are the acoustic pressure in the hole, P, the volume flow through the lead openings, U, and the displacements of the blow and draw leads, XP and XD. These satisfy Bernoulli's equations of motion and the resonance equation on the mouth side. Here, P0 is the blowing pressure, and S is the sum of the two reed opening areas, each of which is a simple function of the corresponding displacement. Here, I'm showing simulated waveforms. On the left, we have normal blow C with no pitch bend, which occurs when the tube length is 100 mm. Both reeds oscillate sinusoidally at the same frequency, but the blow reed has a larger amplitude. When it is closing, that is when the displacement xt is decreasing, the pressure peak has a peak and it drives the reed. On the right, the tube length is extended to 170 mm and pitch bending occurs. The draw reed takes over and oscillates with a large amplitude than the blow reed. Here on the right, the simulated pitch bend is shown, and on the left, the actual pitch bend observed in the experiment is again shown for comparison. The agreement between these two is remarkably good. Johnston theoretically predicted pitch bending by comparing the admittances of the reed and the mouth side resonator. Improving his method, I predicted the sound frequency. The result is shown on the right, and the simulated frequency is shown again on the left for comparison. Although the prediction does not capture the deepest pitch bends, the agreement is quite good, given that it relies on a small amplitude approximation. Let me explain more how the sound frequency is predicted. In this figure, the reed admittance is plotted in blue, and the resonator admittance is plotted in orange. The upper panel shows the amplitude, and the lower panel shows the phase. The necessary condition for sound production is that the amplitude of the reed admittance, blue, is larger than that of the resonator, orange. When the harmonica is sounding steadily, the two phases should match. When the tube length is 100 mm, the amplitude condition is satisfied here. In this frequency range, the two phase curves intersect here. This is the predicted sound frequency. As the tube is extended, the resonator's resonance frequency is decreased. Along with this, the two phase curves intersect here at a lower frequency. This explains how the pitch bending occurs. Let's move on to overblowing. The left figure shows the note G played normally on hole 6, and the right figure shows B-flat overblow. The normal blow occurs when the tube length is 100 mm, while the overblow occurs when it is shortened to 40 mm. In this case, the draw reed oscillates with much larger amplitude. This slide shows how the frequency varies depending on the tube length on hole 6. The left figure is a simulation, the right figure is a prediction. These two again match well. The pitch jumps if the tube is shortened from 100 to 40 mm. This is overblowing. This slide shows the admittance curves for hole 6. The normal blow is on the left and the overblow is on the right. For normal blow, the oscillation conditions are satisfied at this intersection, while for overblow, they are satisfied here at the higher frequency. As the tube is shortened from 100 to 40 mm, anti-resonance peak of the resonator scans the reed admittance peak from here to here. from here to here. During the scan, the amplitude condition is not satisfied. This explains well why choking occurs between the normal blow and the overblow. Let's summarize the talk. Johnston's experiment was reproduced and pitch bending was confirmed. A harmonica sound production model for simulating pitch bending and overblowing was proposed. Pitch bending on hole 7 is simulated remarkably well with this model. The phenomenon is also well predicted theoretically by examining oscillation conditions. Overblowing is successfully simulated and predicted. The choke between the normal blow and the overblow was also well explained. In this study, we clarify the physical mechanisms of pitch bending and overblowing. The next challenge is to understand how players actually control the shape of the oral cavity. I look forward to further progress in this direction. Thank you for your attention. I hope you enjoyed this video. See you next time.